All right, so power is one topic you'll get into. It's pretty straightforward. Power is simply the rate of change that work or energy is done. And so power is defined as the amount of change in energy per time or the work per time. Remember, work and change in energy are the same. So, like, it's either one of those or the other. Now, one of the things they've been doing more is just make sure you understand, and just so you understand, this work can also be written as like, right, the force, like the work calculation we do. And if you look at this portion here, like if you, all I did from there to there was just replace the work with force times the displacement. This part's actually velocity. And so power can also be related by force times velocity. Now, I don't know if this equation not normally given on the equation sheet, but it's something to understand and it's sometimes useful. This could be the instantaneous power because the force and the velocity may vary over time. Okay, so this is not necessarily like if either of these are not constant, then you just think of this as the instantaneous the power at a particular moment in time. The whatever force is acting on it times the velocity, how fast it's moving, is how much power is being delivered by that force. Okay, and how much work. Now, power, units of power. Remember, work and energy is in units of joules, is joules per second, which we call watts, or we use W for it. So watts is our units for that. Again, named after someone, you get famous enough in physics, you get units named after you. Okay, that's the rule. So let's continue on, like some examples. So we have a motor. It lifts a 60 kilogram box at a constant speed using a rope. What is power delivered by the motor? So we need to know what force it is. So we're going to use that force times velocity to for the power there. We got to think about like it's lifting it at a constant speed. So what are the forces acting on it? Well, we got mg. Remember, we got to start with a lot of free body diagrams most of the time. You're going to have something, it's lifting it, right? So it's force from the motor here. Now it's constant speed, so the acceleration is 0, which means that these two forces cancel each other out. We know the motor force, if we say up is positive, we do F net equals ma minus mg is equal to 0. That's my F net equals ma, right? So that means the motor force has to equal mg. And so the power by the motor is whatever the force is the motor times the velocity. And it's constant velocity, so we already know that. So it's going to be mg times v. So that's going to be 60 times 10 times 1.2. If I use, you can use 9.8 if you want, but 10 is fine. So what is that? 12 times 60, what, 720 watts, like that. Okay, let's take a look at another example. Student pulls a 15 kilogram sled up a snowy hill at incline of 20 degrees, right? So we have a sled here. It's being pulled. The coefficient of kinetic friction is 0.1. The sled is pulled at a constant speed of 2.5 meters per second. Find the power output of the student. So constant speed means the acceleration is 0. So we got to draw our free body diagram. We have mg. We have a normal force. And he's pulling it up the rope. Now, here's the question. Is he pulling it up the rope? Is he pulling in this direction? Doesn't really matter because for the purposes of work calculation, we only care about the force parallel to the displacement. So it doesn't really matter. But let's assume, actually it does matter because there's friction. He's pulling it up the ramp. So he pulls, we'll just say he's pulling in the same direction. I didn't put it in the question, but I wrote the question. So let's just assume he's pulling it in there. So we're done with our free body diagram. Those are all the forces, right? And we want to know just the power from, do this. Sorry, let me make this a little bit bigger because we're going to do some decomposition. We want the power output of the student. So we want to know the power by this force right here, okay? So again, the power by the student is going to be the force that he's pulling times the velocity. We already know the velocity, so we can kind of figure that out. So we need to figure out what this force is. Well, we know the acceleration is 0, so we got to decompose all our forces. And the acceleration, it doesn't really matter, but we'll go and make this the x direction and this the y direction. Why do we do that? Because I don't want to decompose as many forces. Technically, the acceleration is 0. I can decompose anyway, but might as well just do it. This is the simplest way to decompose it. This would be mg cosine 20 degrees. This would be mg sine 20 degrees. Okay. So now let's do x direction F net equals ma. So x direction F net equals ma, which is 0. We'll say up the ramp is positive. We have the pulling force up the ramp. We have frictional force down the ramp. And mg sine 20 degrees is pointing down the ramp. So that is also, okay, that equals 0. In the y direction, right? The reason I need the y direction is because I don't know the frictional force, right? I need to solve for the pulling force, right? Which is the frictional force plus mg sine 20 degrees. But I also need to solve for this guy right here, which is mu, because it's kinetic friction, mu times the normal force, so I need the y direction here. Acceleration's also 0 for this one. We'll make this direction the positive direction in the y direction. That'll be Fn is up the ramp, mg cosine 20 degrees is down the ramp, or not, is perpendicular out of the ramp, perpendicular into the ramp. That's equal to 0, so the normal force is mg cosine 20 degrees. And then we can solve for that frictional force is mu k times the normal force, which is mg cosine 20 degrees, just like we did in Unit 2, right? So we're doing the exact same things we did in Unit 2. And so then the power is just going to be this thing. Let's factor out a mg. And then times the velocity is going to be that power. So that's the expression here. Now we just got to plug in some numbers here. So that's 0.1 cosine of 20 degrees plus sine of 20 degrees times mg, which is 15 times 10 times 2.5. And then we'll just use the calculator to solve for that portion, right? So 0.1, make sure you're in degree mode. I am in degree mode. Sine 20 degrees times 150 times 2.5. And I get about 163.5 watts there, just like that.